So in this portion of the video, we'll discuss the concept of linear dependence. So recall this particular linear combination adds up to the vector 1, 2, 3. We'll abbreviate this as 3u plus 2v equals w, just by using a normal natural definitions for u, v, and w. From this equation, you can see that in some way w just depends upon u and v. If you knew the linear combination, you would know what w equals. At the same time, though, you could solve for u and see that u is a linear combination of v and w. So u depends upon v and w. In order to get around this question of what depends on what, we're going to define the concept of linear dependence. So a set of vectors, v1, v2 up to vk, is called linearly dependent if and only if there are scalars, not all which are 0, so that when you form the linear combination of those vectors, it equals a 0 vector. Notice it only insists that at least one of the scalars is 0. A set of vectors that are not linearly dependent are called linearly independent. Now, again, to make it very clear to you, if at least one of the scalars is non-zero in this linear combination, if you can find one such linear combination of 0 where one of the scalars is not 0, we say the set is linearly dependent. If the only linear combination of these vectors that adds up to 0 is where the scalars are 0, that set is called linearly independent. Now, the linear combination where all the scalars are 0, of course, equals a 0 vector, but we call that particular linear combination the trivial one because we know that one. We know that one adds up to 0. So we're often looking for a non-trivial linear combination of 0 in order to show that the vectors are linearly dependent. Now, linear dependence requires at least one coefficient of 0. A number of them can be 0. Sometimes because of that, then, you can find a really simple, non-trivial, at least one scalar is not 0, linear combination of your vectors that adds up to 0 just by looking at it. This is called by inspection. For example, if you look at the vectors 1, 2, and 3, 6, obviously one vector is 3 times the other. So if you take 3 times 1, 2 and subtract 1 times 3, 6, you get the 0 vector. So that means then that these two vectors are linearly dependent. A little more tricky, if you look at these three vectors, 1, 2, 0, 0, and 1, 0, notice you can multiply the vector 0, 0 by 1, which is not 0, and multiply the other scalars by 0, and you get a non-trivial linear combination of these vectors that adds up to the 0 vector. So those vectors are linearly dependent. Recall again that linear dependence just requires that one of the scalars in that linear combination is non-zero. So that implies then if you ever add vectors to a set of linearly dependent vectors, the result is also always linearly dependent. Just because of this. For example, look at these two vectors. They're obviously linearly dependent because they're multiples of each other. So 2 times the first vector minus 1 times the second is going to be the 0 vector, and that is a non-trivial linear combination that adds up to 0 because at least one of the scalars is non-zero. If you then throw another vector in, notice you can use pretty much the exact same linear combination, same scalars, but for the scalar for the new vector, just put 0. The result is still 0, and that is a non-trivial linear combination of those vectors that adds up to the 0 vector, because at least one of the scalars is non-zero. Some of them can be 0. As long as at least one of them is not, it's considered to be a non-trivial linear combination. If I add on yet another vector, for that new vector, I can throw that into the linear combination just by putting the scalar 0 in front of it. This new linear combination of these 4 vectors still adds up to the 0 vector, and notice it's a non-trivial linear combination because at least one of the scalars is non-zero. So as a really quick observation of what I just noted to you, any set of vectors that ever has the 0 vector in it, that set is instantly linearly dependent. It's pretty obvious by looking at it one way. The vector 0 by itself, if it's ever in the set, just by itself, that vector is considered to be linearly dependent because of the definition. Because if you take a non-zero scalar, any non-zero scalar, and multiply it to the 0 vector, that linear combination of that one vector equals 0. So it's a non-trivial linear combination that adds up to the 0 vector. So the vector 0 by itself is considered to be linearly dependent, even though there's only one vector in it. But then the minute you have that, since that one set is dependent, if you add any number of vectors after it to that set, the resulting set is then also linearly dependent, using the exact same trick you saw me do on the previous slide. So for example, the vectors 1, 2, 0, 0, and 1, 0, the example you saw before, that is instantly linearly dependent because it has the 0 vector among that list. Now, let's soup up our method of inspection by a little bit. To begin this topic, we notice there's a connection between U is a linear combination of V and W, and the vectors U, V, and W are linearly dependent. I'm just going to formalize that idea. So this theorem, it's called Theorem 2.5 in your book. The vectors V1, V2 up to Vk in Rn are considered to be linearly dependent if and only if at least one vector can be expressed as a linear combination of those that are also in that set. You also, if you want, can throw in the it's a linear combination of the vectors that occur before it, if you want to, because you can just reorder the vectors in order to make that true. Now, please notice that I choose not to prove that theorem. The reason is it's so incredibly evident that if you just look at a couple examples, you can see why it's true in all ways without doing symbols. So I'm going to forego a formal proof. Instead, look at this example. Notice that these vectors are linearly dependent because I can form a linear combination of them that is not trivial, that adds up to the 0 vector. But if you wanted to, you could solve for the first vector, and when you do so, you get one vector is a linear combination of the other, or at least some of the others. Doesn't have to be all of them, just any of them. So then looking at the other way, this one vector is a linear combination of two others. But then if you were to bring all the vectors to one side, you can see that those three vectors are linearly dependent because they, well, form a linear combination that adds up to 0, and that linear combination is non-trivial. So then this theorem is just a matter of, do you solve for a vector or you don't, if you have 0 on the other side. Now, as another really quick consequence then of that theorem you just saw, if two vectors are linearly dependent, that can happen if and only if one is a multiple of the other. We've already used this now twice or 3 times. This one I'll really quickly prove. Suppose that one vector is a multiple of the other. So a multiple means, some scalar. That means then instantly, just by definitions, that V1 is a linear combination of V2. But from our previous theorem, Theorem 2.5, since V1 is a linear combination of V2, that means that V1 and V2 are instantly linearly dependent. So this is great because it means that you can look at two vectors and instantly know if they're linearly dependent, or more importantly, linearly independent, just if they're multiples or not. So these two vectors are instantly linearly dependent because they're multiples of each other, while these two vectors are not linearly dependent. So we call them linearly independent. And that's the first time we've used that because one is not a multiple of the other. You cannot hope to get questions that are as easy as, are these two vectors linearly dependent or independent? Because if they're multiples, they're dependent. If they're not, then they're independent. That's easy. Or look at the set of vectors that contains the 0 vector. Are these vectors linearly dependent or independent? Because since they contain the 0 vector, they're automatically linearly dependent. We need some kind of technique, some computational device that if you give me a bunch of vectors, I can use Gaussian elimination in order to go and determine whether the corresponding vectors are linearly dependent or independent. So let's work with an example that we know the answer already. These two vectors here we know are linearly independent because they're not multiples of each other. But let's go do it by using the definition. Now, if they're linearly dependent, that means there must be a non-trivial linear combination that adds up to 0. So let's just find all possible linear combinations that adds up to 0. I'll prove to you the only such linear combination that exists is where all the scalars are 0. That means then the vectors have to be independent. So let's just find all such scalars so that this linear combination of these two vectors adds up to the 0 vector. Now, using a trick you saw before from 2.4, this linear combination corresponds to this linear system, which we call a homogeneous linear system, and that corresponds to this augmented matrix. They are all connected to each other. Here, this particular augmented matrix has this particular RREF. By looking at this and then going back to the system, you can see the only solution is C1 equals C2, which is 0. So then, since the only possible scalars where this linear combination equals 0 is where all the scalars are 0, the vectors then are linearly independent. It's really easy. It's very similar to what we did before with spanning sets. It's just slightly different, slightly changed. Let's try it again. A little more complicated. Let's look at these 4 vectors from R3. I'm going to show you that they have to be linearly dependent. So to do so, let's just find all possible linear combinations, all scalars, so that the linear combination adds up to the 0 vector. All I have to do is to convince you that there's at least one non-trivial example. So a clever way to do that is that if I can show you that when you look at the corresponding system, that the corresponding system has at least one free variable, you could then declare that that free variable is not 0, then all the others will be determined, 0 or not, and that will then form a non-trivial linear combination of these vectors that adds up to 0, because one of the scalars, the free variable, will be not 0. So as you've seen before, this particular linear combination that adds up to 0 corresponds to this corresponding linear system, which is homogeneous, and that corresponds to this augmented matrix, and I just instantly row reduced it to its reduced row echelon form. But from here you can see though that C4 would be a free variable if you go back to the system. So since C4 would be a free variable, I'll make C4 be 1, and all the others will then be determined based upon it. That then gives me a linear combination of the original vectors that is not trivial, because at least one of the scalars is not 0, that adds up to the 0 vector. These vectors are linearly dependent. Theorem 2.4 was really useful in order to cut down the amount of writing an argument when we wanted to know if a certain vector was a linear combination of others, or if a vector was in a span of others. So let's just do basically the same thing for this case. It's a direct analog of that theorem, just for this one special case. So we'll call it Theorem 2.6. It's in your book. A homogeneous linear system with augmented matrix A/0 vector, so the 0 vector is just the last column, has a non-trivial solution if and only if the columns of A are linearly dependent. And if they are dependent, then any non-trivial solution to the corresponding system using the coefficients C1, C2 up to Cn provides the coefficients in that linear combination. So this proof is really straightforward, and you need to start getting used to seeing these to understand when we get to the more difficult ones where example really won't pave the way for understanding. So the vectors v1, v2 up to vn, let's suppose that they are linearly dependent. Now that can happen only if and only if there are scalars, not all 0, so the linear combination of those vectors is the 0 vector. But we can go directly from Theorem 2.4 to say that can happen if and only if that the corresponding linear system whose augmented matrix is A/0 has a non-trivial solution. And that's it. Now to go ahead and use it, let's do it quickly. I want to show that these vectors are linearly dependent. So instead of going through all the little hoops we did before, we can kind of skip right to it and say, just consider the homogeneous system corresponding to the following augmented matrix. Its row reduced echelon form is this. That means then that such a linear system will be consistent because it's homogeneous, and it will possess a free variable. So there are non-trivial solutions. So that means that these vectors are dependent. But if you'd like to go a step further and find out what are those scalars, you could do so. All you have to do then is write down the corresponding system, choose the free variable to be not 0, any free variable to be not 0, and then determine what the rest of the values are. That will then give you a linear combination that will add up to 0, where at least one of the scalars is not 0. So you might notice that from the previous theorem, 2.6, that if we get the question of whether our vectors are linearly dependent, that corresponds to looking at a particular homogeneous linear system and asking, does that system have a free variable? Are there an infinite number of solutions? Because then there's at least a non-trivial one. Well, but in one circumstance from a theorem we've already studied, as long as the homogeneous linear system has more variables than it has equations, then instantly the system has an infinite number of solutions. So we can combine these ideas to get this result. If you ever have a set of m vectors from Rn, and m is more than n, so there's more vectors than the dimension of the space, then they are instantly linearly dependent. That's great. We can't use this result, unfortunately, to show something is linearly independent, but we can use it quickly to show something is dependent. Once again, you need some experience with proofs before we get into the more serious ones, where you just simply can't see the result by example, not in general. So, let's assume that we have a bunch of vectors, m of them, that are from Rn, and m is more than n. Well, now just form a matrix A whose columns are these vectors. And look at the corresponding homogeneous linear system, A adjoined with that 0 vector. That thing has got to have a non-trivial solution, because from a previous theorem, this particular system will have more rows, more variables, than it will have equations. The number of columns in A is more than the number of rows in A. So therefore, there has to be a free variable, and so there is an infinite number of solutions to that system, and so there is at least one non-trivial solution. So by theorem 2.6 then, since there's a non-trivial solution, the vectors that make the columns of that matrix are instantly linearly dependent. Neat, right? So we can use that this way. Remember this example, I just did it? These are 4 vectors from R3. They are instantly linearly dependent. I don't need to go through the work to prove it. I already know it will be. So if I have 3 vectors from R2, those vectors will be linearly dependent. If I had 10 vectors from R5, those vectors are instantly linearly dependent. If I had 3 vectors from R3, then I don't know. If I have 2 vectors from R3, then I don't know. So we've answered the question whether a set of vectors are linearly dependent or independent by looking at a corresponding homogeneous linear system whose coefficient matrices columns are just the vectors. That's really useful because it's very similar to everything we've done. But there's also a way to do the exact same thing by looking at rows instead, treating the vectors as rows. The disadvantage is that you can't figure out what the coefficients are very easily. If you want to figure out what is the linear combination, that's the non-trivial linear combination to show the vectors are linearly dependent. It's much more challenging. Can be done, but it's more challenging. The good thing is, though, it's faster. It's just a little bit faster. If the only thing you want to know is if the row vectors are linearly dependent or independent, it's pretty quick. It's based upon this simple idea. What if you perform one row operation on a matrix to result in another matrix B? Thing is, though, is that any such row operation will just replace a row of A to be a row of B by forming a linear combination of the rows of A. The reason this is because the order of the vectors doesn't matter, so the swapping row operation doesn't do anything. If you take a multiple of A to get a row in B, well, then that new row of B is a linear combination of the vector you just used. It's a multiple of it. And the third one is, if you replace a row in B with the ith row of A minus a constant times the jth row of A, well, then the new row of B is literally, just by the way we just said it, a linear combination of the vectors of A in the rows of A. So that leads us to a really nice theorem. If you just repeat this over and over and over again, you'll notice that a sequence of row operations will result in the following: that if A and B are row equivalent, then the rows of A are linear combinations of the rows of B, and because row operations are reversible, vice versa. The rows of B are linear combinations of the rows of A. It's a really nice result that we're going to abuse quite a bit in future chapters. So proving that theorem formally is a little tedious. And because of that, I'm going to save it for another day. That will be for a future portion of the course when we have just a little bit more machinery under our belts. So let's just look at an example. And by looking at the example, I think you'll go, oh, that's why the theorem is true. So let's look at 3 vectors. Consider them as row vectors, and then form a matrix using those particular row vectors. The order of the rows completely doesn't matter. I don't care. We're now going to look at some kind of row equivalent matrix to A. What row operations we use completely don't matter. What the ending form of the matrix is when we're done these row operations doesn't matter, because it doesn't matter in the theorem at all. But because almost always we row reduce to either a row echelon form or a reduced row echelon form, I'll aim for one of the two. So here, take this matrix and perform these 2 row operations in order. That will give us a new matrix, which I'll just call C to make it easy. Also, the rows of A we call R1, R2, R3, but I need to talk about the rows of C also. So I'll call them R1 prime, R2 prime, and R3 prime. Then from here, I'll perform another row operation to get the matrix B. And again, B has rows. I have to call them something. I can't call them the same thing I did before. So I'll call them R1 double prime, R2 double prime, R3 double prime. Notice that R1 prime and R1 double prime, they're the same. And R1, R2 prime and R2 double prime is also the same, because the first rows of B and C are equal, the second rows of B and C are equal, but the third row of B and C are not equal. Okay, now you have this. Focus on any row of B, and all you have to do is just trace backwards, literally using equations in these row prime statements. So the third row of B happens to be the 0 vector, but that's R3 double prime. But that's equal to R3 prime minus 2 times R2 prime. But I know that those rows, R3 prime and R2 prime, those are the rows of C. And I know the rows of C in terms of the rows of A. I just plug that in. And then I just collect terms. And that means that 0 is a linear combination of the rows of A. So the third row of B is some linear combination of the rows of A. That means then that I know then that at least the third row is linearly dependent upon the rows of A. And you can reverse this too, by the way, because remember, all row operations are reversible. So you can repeat this process to show that any row of A is some linear combination of the rows of B. It's just the third row of B doesn't matter because it's a 0 vector in that linear combination. Also, though, notice, also kind of neat, notice that I just showed you that the rows of A, there is a linear combination that's not trivial that adds up to the 0 vector. That means then the rows of A are actually linearly dependent. This is a new way to show that a bunch of vectors are linearly dependent. All I'm going to do is take what you just solved, this one example, and turn it into a theorem. And then we just use the theorem from here on out. So we call this theorem 2.7 in the book. Let V1, V2 up to Vm be a bunch of vectors. Treat them as row vectors. Form a matrix with those rows. The order of these rows does not matter. Then those rows, those vectors, are linearly dependent if and only if the rank of A is less than m. Now, remember, to find the rank of A, you have to find at least a row echelon form, and then the rank of A is the number of non-zero leading entries, or just the number of leading entries. So here, to do the proof really quickly, those vectors are linearly dependent. And that would be then if and only if, or in this case, only if, one vector is a linear combination of those that come before it. Because you can reorder by swapping if you need to. Without a loss, just pretend then that Vm is this particular linear combination of the vectors that come before it. If you then perform these row operations in order, Rm minus C1 R1, Rm minus C2 times R2, and so on, where R1, R2 are just the rows, v1, v2, so on, and c1, c2, and so on are just the coefficients in this linear combination, it will always wipe out one row. The row Rm will now be a row of zeros. If the mth, or if any row becomes a row of zeros, then the number of leading entries will be less than the number of rows. So the rank of A has to be less than the number of rows. That's it. And the proof is reversible very easily. So let's go ahead and use it. I'm going to show you that these particular vectors are linearly dependent. Just form a matrix with those vectors, row reduce it, getting it reduced row echelon form is fine, because the only thing I need is the rank. So the rank of this matrix is 3. The number of rows is 4. So therefore, instantly, the vectors are linearly dependent. If you want to know a linear combination that's not trivial, that adds up to 0, well then I'd have to trace through all those row operations. That means I'd have to do the row operations by hand, because I need to know what row operations I used and when. So that if you want to know the linear combination, this particular theorem is not useful. You really should do the first technique. If all you want, though, is are they linearly dependent or not, it's great. You literally just do the row operation. Just find the reduced row echelon form, and find out if the rank is less than the number of rows. If it is, they're linearly dependent. If it's not, if the rank equals the number of vectors, the number of rows in this case, then they're linearly independent. All right, and I believe that's enough. That's enough to give you a basic understanding of linear independence. And since the first part was about spanning, you have enough for the basic language for building new objects. Remember, when we did this, we were aiming to try to generalize the idea of forming a plane, but with just more vectors and with a larger ambient space, not just R2 or R3.